time for my first linear algebra final to go through. This is fall 2017. We're going to do the entire thing and try to keep it under an hour. We'll see how that goes. Question 1. A is that 2 by 2 matrix right there. Which of the following statements is false? Let's see. Let's just go through them one at a time. For arbitrary 2 by 2 matrices B and C, BA equals BC, then A must equal C. So this is only true if there is some B inverse such that we can say B inverse times B times A is equal to B inverse times B times C, because both of these B inverse B's will cancel out to the identity matrix and we'll have A equals C. But because B and C are arbitrary, we cannot say that they are invertible. We can't guess anything about them other than that they're 2 by 2. So this cannot be true. Let's see, if this is, here's our matrix A. We know this to be invertible because its determinant is non-zero. It has a determinant of -3. And likewise, A transpose must be invertible. We can take A transpose, and that gives us 3, 2, 0, -1, which gives us the same determinant of -3. So that is also true, so it's not our correct answer choice. C, for arbitrary matrices B and C, AB equals BC, then B equals C. Well, this is true. We know A to be invertible. We can play the same little game we tried to do with A and say A inverse A multiplied by B is equal to A inverse A multiplied by C. This simplifies down to B equals C. And so this is in fact true. Sorry. Oh, look, I've been thinking about this wrong the whole time. We're looking for the statement that is false. We already found that A is false. B is true, C is true, D is definitely true. We know that to be a true property. And also, let's see, A inverse is an upper triangular matrix. Let's quickly disprove that. Well, we know that when we take our inverse of a 2 by 2 matrix, we switch the positions. Of let's see, I'll rewrite this. We have our A, B, C, and D positions. When we take our inverse, we'll have 1 over AD minus BC multiplied into DA -C -B. And because this C position doesn't move and all of our other terms are non-zero, and we're multiplying by 1 over some non-zero number, our A inverse will also be an upper triangular matrix. This spot will still be a 0, so all the elements under our main diagonal are also still 0. So 1 is A. 2. For a real number A, consider this system of equations. Which of the following statements is true? So let's put this into matrix form and solve it a little bit. We have 1, 1, 1, 2, 2, 3, 3, 4, and 2, 3, A squared minus 1, A plus 2. Let's subtract, let's see, 2 row 1s from row 2. That will give us 0, 1, 1, 0. And then let's subtract 2 row 1s from row 3. 0, 1, I said 2, right? Yeah, 2. A squared minus 3 now. And over here we'll just have A. Now what? Let's subtract row 2 from row 3. Row 2 from row 3, that gives us a 0 here and a -4 here. And at this point we should be simplified enough that we can figure something out about this system. What about A? If A equals 3, then the system is inconsistent. Well, if A equals 3, nothing particularly bad happens. The only thing that we're really worried about is if we get a 0 here and a non-zero value here. And that will lead us pretty quickly to, let's look at E. If A is equal to -2, then this will be 0 over here and -2 over here. That's saying that 0x plus 0y plus 0z equals -2, which is an inconsistent statement. 3, let A be an n by n non-singular matrix, which means it is invertible. So A inverse exists. There we go. Which of the following statements must be true? The determinant of A is not equal to 0. Yep, I agree with that, because in order to have an inverse, we need to take 1 over the determinant of A, and if that is 0, then we're going to have some real problems. 3, AX equals 0 has infinitely many solutions. No, that's untrue. It will have only the trivial solution, and you can kind of think about this in the sense of the null space of a invertible matrix is zero-dimensional. It only includes the origin, and that's because during our transformation, an invertible matrix's transformation has to go from Rn, all of Rn, and have one unique solution for all of Rn, back to Rn after the transformation, and there must be exactly one unique solution for every point in that output space as well. So there are no extra points getting smushed onto the origin, the 0 vector. So this is untrue. 4, AX equals B has a unique solution for every n vector B. And that's exactly what I was just saying. So if we have some invertible matrix, by the the rules that we use to talk about the properties of matrix transformations, a invertible matrix must have must be reducible. I think I'm not drawing the right number of zeros. Yeah, actually, no, I think I missed one. An invertible matrix, no, that's still wrong. An invertible matrix must be reducible to the identity matrix. And so you can see it has pivots equal to the number of rows and the number of columns. So we know that its columns must be linearly independent, and if we take that I for independent and flip it on its side, our matrix transformation must be 1-to-1 as a result. Additionally, any 1-to-1 transformation, if it's an m by n matrix, must also be on 2, because we have a pivot for every row, which represents each dimension in our output space. So therefore we span the output space, so our transformation is on 2. And having a unique solution for every n vector B really is just asking, is the matrix transformation 1-to-1? Which we said, yes, it is. All invertible matrices will be both 1-to-1 and on 2. What about 5? A must be row equivalent to the identity matrix. Well, I just mentioned that a second ago. You can try that with any invertible matrix that you want, and you'll see that it is true. So we get 1, 4, and 5. C is our answer. 4, we're looking for the 2, 3 entry of A inverse. In order to find any entries of A inverse at all, we're going to need the determinant of A, which will be 1 times the determinant of this submatrix, minus 2 times the determinant of this submatrix, plus 3 times the determinant of this submatrix. And for all these steps, for example, for this 3, we're just multiplying it by the submatrix formed by crossing out the row and the column that 3 is in. Additionally, you'll want to remember that the pluses and the minuses are coming from this whole scheme that we use here, which can come in handy for some of the bigger determinants that they make us take. And this determinant will be, as we said, 1 times the determinant of 1, 1, 2, 2, minus 2 times the determinant of 1, 0, 2, 2, plus 3 times the determinant of 1, 0, 1, 1. Replacing these determinants, we get 1 here, we get 2 here, and we'll get 0 here. So negative 4 plus 3 is just negative 1. So if we're looking for the 2, 3 entry of A inverse, that will be 2, 1, 2, 1, 2, 3. That will be this entry here. We know that eventually in taking our inverse, what will happen is that everything that we've computed at the very end will get flipped or transposed. So reflected along the main diagonal. So what we can do is find the cofactor at this position, the 3, 2 position, knowing that that will end up getting flipped over to the 3, 2 position eventually, and that will be our answer. So the cofactor for this position is just this sign outside of the determinant of the matrix formed by crossing out the row and the column that we care about, which in this case is 3, 2. So that leaves us with negative 1, 1, 3, 2, that determinant, which is 2 minus 3, negative 1, so positive 1 there. And then we have to divide by our determinant in the end, and we get an answer of negative 1. It's a little convoluted, and there are much better explanations of how to, full explanations doing a 3 by 3 inverse, that if what I just said made no sense, which I'm sure in many ways it did, please go look for those. That would be a good decision. Okay, 5, we're finding the determinant of this matrix. We know that if we have a matrix in upper triangular form, so we have some entries down the main diagonal, but then zeros everywhere else under it, that we can find our determinant just by multiplying all of those main diagonal entries together. What we also know is that if we take 2 rows or columns and switch them, that we'll multiply our determinant by negative 1. And so what we can do is take our first column and fourth column and switch them, and then take our second column and third column and switch them, and we'll be left with 1, 0, 0, 0, 0, 2, 0, 0, 2, 4, 3, 0, negative 1, 3, negative 8, and 4. And so switching 2 columns just multiplies our determinant by negative 1 twice, so we've done nothing to our determinant in the end, and now we're in upper triangular form, so we can just multiply these entries and get positive 24, which is 5, and it's correct. We're told that AD minus BC equals 2, and that C is equal to 2A minus 4. Let's find the value of y determined by this linear system. So you can do this one of 2 ways. You can either find the inverse of this matrix over here and multiply the left side of both sides of our equation, by that inverse, and that will allow us to just solve directly for x and y. But what we're going to do here is use Cramer's rule, which is a little bit of an easier way. Whenever we have a system like this, we can say that, for example, y is represented by this fraction. It is the determinant of this matrix if we replace the y column, which is this BD here, with whatever x and y multiplied by that matrix are equal to. So that means we'll have A, C, 1, 2, and then we just divide by the determinant of this matrix with nothing done to it. This gives us 2A minus C, all divided by AD minus BC. Since we know that AD minus BC is equal to 2, we can replace that. And let's rearrange this expression to tell us what our top thing there is going to do. Let's subtract 2a and multiply everything by -1. Subtract 2a to the left side, sorry. And we will have 2a minus c is equal to 4. So we'll replace that up here, and we see that our answer is 2, 4, 6. And by 2, I mean b. There we go. 7. If A is this complex valued matrix here with an inverse with entries A, B, C, D, then what is the sum of A, B, C, D? So we don't really have to care about fully writing out A inverse, but what we do have to know is how the signs of our different entries of A are going to change and what our determinant will be. So finding our determinant, that's AD minus BC, that will give us 1 plus I minus 1. This is the determinant of A, and that's just I. So what we can do is take 1 over that determinant, because 1 over the determinant will be multiplied into all of our entries for our A inverse, and then just add up our 4 entries for A inverse. We know that our A and D positions will just switch places, so their signs will not change. We can write 1 plus I, but that these two positions will change sign, so we get -1, -1. This gives us I over I, or just 1 for 7. It always scares me when you have this, this outlier real answer and then a bunch of complex ones, but sometimes you just gotta believe. Okay, 8. Consider the following subsets of the vector space R4, which are subspaces of R4. Right off the bat, I can see that 2 of these are perfectly fine subspaces, and one of them is not. The one that is not is this guy right here, and the easiest way to see that is that there is no solution, no value x that you can plug in to get the origin, because this 1 will always be there no matter what. So we don't pass through the origin, and thus our space, or the span of this vector, is not closed under scalar multiplication, because if we multiply by some constant and where that constant's equal to 0, we will jump out of the space, and we won't be in that subset anymore. Looking at A, we can just write this as the span of the vector 2, 3, -1, 5, and anything that we can write as a span is a valid subspace. Additionally, this is just the solution to A times some vector equals 0. So this is the null space of this matrix in R4, and the null space is one of our 4 major subspaces that we talk about. So these 2 are good, middle one is bad. So 1 and 3 is our answer for 8, that's D. 9. Consider the vector space P2 of all polynomials with coefficients of degree at most 2. Which of the following subsets spans P2? Well, in order to span P2, we need to have a leading coefficient for t squared, 1 for t, and 1 for the constants. And since we know that the minimum size of a set that we need to span 3 degrees of freedom here is that same number, that's 3, we know that any of these sets down here that only have 2 entries are no good, so that gets rid of A. Additionally, we can get rid of both B and C, because C has no terms that just have t in them, so that can't possibly span P2. We need some one of these vectors that we can vary to control where we are in the t to the 1 dimension or space. So that's no good. And in the same way, b is no good because it doesn't have any control over the constants. Then setting both of these guys up, d and e in vector form, we can write this as the vector 1, 1, 1. This guy's the vector 0, 1, negative 1, and this one as 2, 3, 1. And let's row reduce this. And what we're looking for is 3, to reduce to the identity matrix, or for us to have 3 pivots. So let's do that. Let's subtract row 1 from row 2, 0, 1. Let's add row 2 to row 3, 0, 2. And then already we're seeing that that's no good, because if we subtract row 1 from row 3, we get a row of zeros, which is no good at all. So that means that we only have 2 pivots, and that therefore that does not span P2. Setting up our final one, 1, 0, 4, 1, 2, 0, and 0, 1, 3, we can row reduce this, subtracting 4 row 1s from row 3, 0, negative 4. And since we have a pivot here, and these two kind of sets of terms are not linear combinations of each other, we are perfectly good, because if we add 2 row 2s to row 3, we get 0 and 5. So those are our 3 pivot positions, and we span P2 with option E. 10. Which of the following subsets of R3 is linearly independent? So this time we're not looking to span R3, we're just looking to have 2 vectors that, 2 or 3 vectors, a maximum of 3, that do not lie on each other's span. So things that we can keep our eyes out for, just to cross off answer choices right off the bat, is if we have any full rows of zeros, columns of zeros, or if we have only 2 vectors that are clearly linearly independent, which would mean that they're direct linear combinations of each other. If we multiply this vector in A by 5, we get exactly that second vector in the set. So they lie on each other's span, and A cannot be a linearly independent set. Additionally, for E and B, we see a row of zeros, a row of zeros, and really what that tells you is that the rest of these vectors are trying to fit 3 linearly independent vectors into 2 degrees of freedom, which we can't do. If you have 2 linearly independent vectors that say form a plane, and there's no way to place a third vector using those same 2 degrees of freedom in that space without already being in the span created by the first 2. So those are no good. And finally, D is also no good, because we have this guy multiplied by 2, you get this other vector in the set. So these 2 are linearly independent, these 2 are linearly independent, but 1 and 3 are not. So the set as a whole is not linearly independent. And you can go and row reduce C and see that you get 3 pivot positions, but I'm not going to take the time, just because it's so clear that every single other choice is incorrect. 11. Let's determine all of the values of t such that the following vectors form a basis of R3. So if our vectors form a basis of R3, we want there to be 3 pivot positions in the row reduced form of the matrix formed by squishing all 3 of these together. So let's do that. We have negative 1, negative 2, 2, negative 1, t, 2, and t, negative 3, 2. Let's multiply row 1 by negative 1 just to make the math a little easier. Let's add 2 row 1s to row 2. We'll get 0. We'll get t plus 2 and negative 3 minus 2t. What else can we do? Well, we might be able to figure something out right now, actually. Because if our vectors form a basis of R2, then t cannot be -1. T cannot be -1. And where am I seeing that? Well, if t is -1 here, then we'll have 1, 1, 1 across this row and 2, 2, 2 across this row, which is, clearly no good, because having two rows that are linear combinations of each other means that we can use one to set the other one equal to 0, and thus we're definitely not going to have 3 pivot positions in the end. But let's just show that by subtracting 2 row 1s from row 2. That gives us 0, 0, plus 2t, and that's also where that -1 behavior shows up. Let's add row 3 to row 2. That gives us -1 and gets rid of that entirely. And what can we do here? Well, if t is equal to -2, that's also extremely bad, because if we don't have a pivot position here, there's no other place for us to have a second pivot position for this column, because this guy isn't a pivot position. It's backed up by this pivot position here. This is the only place where that pivot position could exist, so if that's equal to -2, by definition, we don't form a basis of R3 because we won't have 3 pivot positions. So that gives us E as an answer for 11. 12. Let A be a 4 by 5 matrix. 1, 2, 3, 4, 1, 2, 3, 4, 5. So it will be wider than it is tall. And let B denote the row-reduced echelon form of A. Which of the following statements is true? If the 1, 3, and 5 columns have leading 1s, then the columns 1, 3, and 5 of A span R4. If you have a good sense for how spanning a vector space, or spanning a space in general, should work, this should be setting off some sirens in your head, because we know that in order to span R4, we need 4 vectors at a minimum. And so, by definition, 3 columns, it doesn't matter how many entries are in each column, cannot span R4. Okay, B, if the number of non-zero rows of B is equal to 3, then the number of non-zero columns of B is equal to 3. So let's diagram that one out. If we have 3 non-zero rows, that means we'll have a pivot position here, a pivot position, and I really shouldn't draw these as zeros, pivot position, pivot position, pivot position. So you might be tempted, since we know that the rank of A is the same as the rank of A transpose, to say, okay, well this seems right. If our rank is 3, then we could count these 3 on this axis or on this axis, and it doesn't really matter. It's still 3. But this is our row-reduced form of A. There's no reason to believe that we're not going to have non-zero entries elsewhere. And in fact, if we have a 0, on our final row, so that's not a pivot position, we can have whatever we want above it and still be fine. And we can also have whatever we want to the right of it, and it'll still be the row-reduced form. All that we really need for that is for there to be zeros above all of our pivot positions, and we need to have this kind of main diagonal look to it. So no, there can be other non-zero positions, and so if we're counting on this axis, we could see up to 5 non-zero columns, where we only see 3 non-zero rows over here. So this is incorrect. C, If B has 3 leading 1s, then the nullity of A is 3. So B having 3 leading 1s is the same thing as saying that the rank of A is 3, and since rank plus nullity, where rank is the dimension of the column space, nullity is the dimension of the null space, that's equal to the number of columns in A, which in our case is 5. So if rank is 3, then nullity must be 2, so C is incorrect. What about D? If the number of non-zero rows of B is equal to 2, then one can pick 2 columns of A such that they form a basis for the column space of A. Well, that's exactly how we find the basis for a column space. We find the row-reduced echelon form and note the columns that have leading 1s in them, so our pivot columns, and then we go back to the original form of A, and the whatever pivot columns we have there, those by definition have to span the column space of A. So D is correct, and we've done that manually many times so far this semester. 13. Which of the following statements are always true? 1. If A is an m by n matrix, then the solution space, the set of x for ax equals 0, is a subspace of Rn. This is just something you kind of have to remember, that the null space, which we know to be the set of all solutions of ax equals 0, is a subspace of Rn, the number of columns of the matrix. And I really, at this point in time, I don't have a good explanation as to why, which is a little sad. But I don't know, however you want to remember that. Maybe n for, oh, there you go, n for null space. Yeah, the null space is a subspace of Rn, n. Okay, so this is true. What about 2? If A is non-singular, if and only if A is the product of elementary matrices. That's also true. And even more so than option 1, I don't have an explanation as to why. I even kind of forget what an elementary matrix is. Maybe that's something for you to go look up. But the nice thing about this class is that we don't have to write essays about this kind of thing. We only have to kind of know these facts. So yeah, no, every non-singular matrix is the product of elementary matrices. That is true. 3. If A is an n by n matrix and K is a scalar, then the determinant of Ka is the same thing as K times the determinant of A. Well, this is untrue, because if we multiply K by some 2 by 2 matrix, A, B, C, D, that's the same thing as multiplying both of the rows or both of the columns by K. So K, A, K, B, K, or CK, I guess, and K, D. And so really what we're going to do when we multiply, if we're trying to find the determinant of a matrix multiplied by some constant, is we're going to take that constant raised to the number of rows or the number of columns of A. So K to the n, in this case, times the determinant of A. And that will give us our expression for the determinant of Ka. So that is incorrect. 4. Let A be an m by n matrix, and the row space of A is orthogonal to the null space of A. This is true. And, you know, like usual, I can't remember the proof, but if I can remember it, and remember it for the exam especially, then I think you can too, and that's really what matters in the end. Yes, the row space is orthogonal to the null space. They like bringing that up almost as much as they like bringing up the fact that the rank of A is the same as the rank of A transpose. And I just circled the wrong answer, so D is correct for number 13. Excuse me, 14. Let's find the sum of the eigenvalues of A. One of the coolest things I still don't know why it works. I have no idea at all why it works. But the sum of the eigenvalues of a matrix is equal to the sum of the main diagonal entries of that same matrix, so the trace of the matrix. And in this case, it's just 9. So if we get this kind of thing on the exam, and you remember that fact, you can sit there feeling good because it just took you 5 seconds to do a question that a lot of people are going to actually work out the eigenvalues for, and they're going to end up, having to factor a trinomial and overall not having a very good time. So that's pretty nice. 14 is B. Let's find the nullity of A, which means a lot of row reduction. So let's get going. -1. Sorry, and I wrote the first term wrong. 1, -2, 0, 3, -4, 3, 2, 8, 1, 4, -1, 2, 0, 4, -3, and 1, 5, 7, 6, 0. Whenever I write something as big as this down, I always have to double check all of my entries. 1, -2, 0, 3, -4, 3, 2, 8, 1, 4, -1, 2, 0, 4, -3, and 1, 5, 7, 6, 0. Okay, we're good. Let's add row 1 to row 3. That looks like we could cancel out a good amount of things. We get 0, 0, 7, -7, so we can make this a 1 and -1. What should we do now? Let's subtract row 1 from row 4. That'll give us a 0, a 0, a 7, a 3, yes, a 3, and a 4. That was a little messier than I would have liked. Okay, I'm doing this in a little bit of a weird way. Let's subtract 3 row 1s from row 2. That'll give us 0, subtracting 3, so adding 6 is 8. Subtracting 3 minus 9, so -8, and plus 12, which gives us 16 here. So we can turn this into 1, 1, -1, 2. And adding row 3 to that, we'll get 0, 1. Okay, looking good. Let's subtract 2 row 2s from row 1. Or sorry, add 2 row 2s to row 1. That gives us 0, 2, and -2 there. Then let's subtract 7 row 2s from row 4. That'll give us 0, 0, -3 here. And then because row 3 and row 4 are just multiples of each other, we can use 1 to make the other 0, 0. Subtracting 3 row 3s from row 1 will give us, hey, wait, no. What am I doing? We're not actually solving ax equals 0. We're just looking for the nullity. And at this point, since we have things in echelon form, not reduced echelon form, but that's fine, we see that the rank of our matrix is 3. And since the rank plus the nullity of our matrix must equal the number of columns, which is 5, our nullity is 2. 15 is C. Yeah, it can be easy to get yourself kind of wrapped up in trying to solve the whole problem when that's not actually what they're asking for. Okay, 16. ABC is orthogonal to both these guys. Which of the following is true? So I learned this one, or when I was practicing it earlier, I just did it with the cross product. And coming out of Calc 3 and having taken, a couple hundred cross products over the past year, is much easier than doing anything linear related. And really the cross product does exactly what we want it to do here. We want a vector that is mutually orthogonal to two other vectors. So I, negative j, k, 3, 4, negative 2, 4, 2, negative 3. This will give us, it'll give us a row vector, but I'll turn it into a column vector. We'll get negative 12 plus 4, so negative 8. We'll get negative, let's see, we'll get negative 8 plus 9, so 1. And then 6 minus 16, which is negative 10. And these guys are equal to A, B, C. Because any vector, A, B, C, should have all the same relations in here as this vector, negative 8, 1, negative 10. And if we go look at option D, if we take A over C, that's negative 8 over negative 10. That reduces to 4 over 5. So that works. 16 is D. (17). We're given a set of three vectors and told that it acts as a basis for R3, and we're trying to apply the Gram-Schmidt process to this basis to find the orthogonal and orthogonal basis for R3. So doing that, we can find our first basis vector. I'll call it V1, and that's just equal to the normalized, and I'll label these two. We'll say U1, U2, and U3. So that will be U times 1 over the magnitude of U. And so solving that, the magnitude of U is root 5, so we can multiply by 1 over root 5 times negative 2, 0, 1. And there we go. There's our first. There is our first basis factor. So A is incorrect. Now finding V2, we need to find U2, which is 2, negative 1, negative 1, and we need to subtract from it the orthogonal complement of U2, I guess, with respect to U1. So essentially what we're doing in here, and we're also going to have to subtract the orthogonal complement of U2 or U1 onto U2. What we're doing here is if we have, some vector and some other vector, we can kind of project the shadow of this vector down onto that second vector. And by finding that this vector representing the shadow and subtracting it out, we're going to be straightening up this second vector so that its shadow is equal to 0. And then by doing that with respect to this second or third vector in our list later, actually no, we won't be doing that, but sorry, with respect to our second vector later, what we'll be doing is kind of, instead of doing this in 2 dimensions, we're really doing it in 3, where we first rotate it so that from one perspective, so from one angle, it's not, it has no shadow onto a certain plane, and then we're rotating it up in a specific way in another dimension to remove the rest of that shadow. And so really by doing this, we are subtracting out. We're subtracting out this second vector here dotted with this first vector here, all divided by the first vector dotted with the first vector, and then we are dividing, not dividing, we're multiplying by that first vector. And really we're using, I'll be more clear. We'll actually write this out. We are taking U2, this guy right here, so 2, negative 1, negative 1, and we're dotting it with our first unit vector. I accidentally said the first vector in this setup here, but really we have to use that unit vector. So 1 over root 5 times negative 2, 0, 1, and then we're dividing by that first unit vector dotted with itself. So 1 over root 5 times 1 over root 5 multiplied by negative 201 dot negative 201. And so computing all of this, and remembering that all of this in the end is getting multiplied by this oh my god, this first unit vector that we found here. So 1 times 1 over root 5, negative 201. We can compute all this, and it's all going to be fine. But you'll notice that since we have a 1 over root 5 squared on the bottom and a 1 over root 5 squared on the top, we can ignore all of that, which makes our lives a little bit simpler. And in fact, you can ignore any factor that you have outside of one of these vectors anytime you do this. So up here we're going to get negative 5, and down here we'll get 4 plus 1, so 5. And so all of this simplifies down to positive 1, and this is going great. If we compute this, we're going to get 0, negative 1, 0, and that is our second basis vector. We would have to normalize it, but since by definition this has a length of 1, we don't really need to do anything. So there is our second basis vector. Now we're just down to 2. If we're computing our third basis vector, that will be this third vector up here minus, so 4, negative 4, 3 minus this vector dotted with our first basis vector divided by that same basis vector dotted with itself multiplied by that basis vector. So doing that, and that's really what we're doing every time. It's not completely in my head yet. That's why it's a little it's still a little hard for me. So finding that dot product, we'll have negative 8 plus 3, so negative 5. And remember, I can ignore whatever we have multiplied out here because it will all get divided out in the end. So negative 5 divided by this first vector dotted with itself, which is just 5, and then we're multiplying it by that first basis vector, negative 2, 0, 1. And so yet again, this is a plus. And then we're subtracting out v3 dot v2, so that's 4. v3 dot, no, I said v3 dot v2. u2, no, look, that's what I did. This should be u3. There we go. u3 dot v2, which gives us which gives us positive 4. I'm so sorry about this. Gives us positive 4, and then we're dividing out v2 dot v2, which is 1, and then we're multiplying by v2, 0, negative 1, 0. So really, in the end, this gives us a plus 4 in here. So computing this, we'll end up with, let's see, we're subtracting 2, so 2, adding 4, 0, and adding 1, 4. There we go. And normalizing this, well, we can factor out a 2 and just get that out of the way. And so really we can just normalize 1, 0, 2, and we'll multiply by 1 over root 5. And we're done. I'm really sorry about this. I'm still not very good with the Gram-Schmidt process. There are so many much better resources you could be using than me for this right now. So go watch the Khan Academy video. That's what drilled it into my head to begin with. Obviously it didn't stick that well, but here we are. So 17 is C. Let's consider R2 as an Euclidean space with respect to the standard inner product, so the normal dot product that we're used to, and let V be the line spanned by 5, 8. So that's really saying that for every 5 units we move on the x-axis, we're going 8 units up. So we can write that as 5, x is equal to 8y, or 8y. 8y equals 5x. There we go. And we're looking for the equation of the line that represents the orthogonal complement, v, I don't know how to say that symbol, the orthogonal complement. So that will be the line perpendicular to this. So you can just do this geometrically and, you know, figure out that this will be equal to 5y is equal to negative 8x, or rearrange it however you want, or you can just note that it has to be expressible in vector terms such that the dot product of the two, the inner product of the two, is 0. So 5, 8 dotted with negative 8, 5 gives us 0, and expressing negative 8, 5 in terms that we're using geometrically over here, that's for every negative 8 units x, we move 5 units y. So subtracting that x term over, we get option C. And also here, you can do the same thing, and we'll get C for 18. 19. Consider this linear system. Which of the following is the least squares solution? X hat? I don't know. I'm not really sure how to read that. Is equal to sum A, B. So when we're solving a least squares problem where we have AX equals B, but there is no solution for AX equals B, our least squares solution will be found by solving A transpose AX is equal to A transpose B. So let's compute A transpose A and A transpose B, and then solve the corresponding system that we get. We'll have 1, 1, 1, 2, 3, multiplied by 1, 1, 1, 1, 2, 3, and that gives us a 2 by 2 matrix, because this is 2 by 3, 3 by 2. These two kind of cancel out, and we're left with 2 by 2, if you want to think about it that way. And this multiplication gives us 3, 6, 6, and 9 plus 5, so 14 there. Then computing A transpose multiplied by B, which is 5, 6, 7, we have a 2 by 3 matrix times a 3 by 1 matrix, so we will get a 2 by 1 matrix, just like they're talking about up here. And this gives us 5 plus 6 plus 7, which is 18, and then 5 plus 12 plus 21, which is 38. Don't worry, I didn't actually do that fast. I remember from working on this problem this morning. So we can set up this system. Since this times A equals this, we can just make an augmented matrix. 3, 6, 6, 14 is equal to 18, 38, and solve this. Let's subtract 2 row 1s from row 2. That will give us 0, 2, and then minus 36, so 2. This becomes 1, 1. Subtract 6 here, we get 12, and divide out that 3, we get a 4. So there's our solution, 4, 1. Is that 19? Yeah, that was. Okay, 19 is A. 20, let V equal R1. So the number line, we can just think of the number line from negative infinity to infinity. Which of the following is a linear operator that acts on V and just goes right back to V, but after some kind of linear transformation? So the properties of linear transformations that are really useful to know for this kind of problem is that linear transformations or operators always map the origin to the origin, and they always keep grid lines evenly spaced and parallel. Parallel doesn't really matter since we're only dealing in one dimension here, but we can use these two rules to figure these out really quickly. If we take the origin, our input x of 0, what happens to the origin after we apply 1, our option 1 to it? Well, it maps to 7. So boom, right off the bat, both C and D cannot be true because it's not 1 is not a linear operator. Then what about 2? If we take the distance between 0 and 1 and 1 and 2 before our transformation, our operator is applied, we see that those grid lines are evenly spaced. But then if we plug in 1 will go to 5, so now we have a distance of 5, and if this was a linear operator, we would expect for the distance between the transformed 5 and the transformed 2 to also be 5. But if we plug in 2, we get 20, which is a much bigger distance in here. Thus, because grid lines are not evenly spaced, this is also no good. So 2 is bad. What about 3? Well, 2x works. If we plug in 0 for that, the origin maps to the origin, and if we run this same test with our grid lines, we see that this just goes to 2, 4. We have an even spacing between all of our elements there, so 3. So B for 20 is our correct answer. 21, if this is our matrix A, then really what we're doing is finding what eigenvalue -I1 corresponds to. Finding our eigenvalues is as simple as solving the determinant of A minus lambda I equals 0, so we'll get negative lambda multiplied by negative lambda plus 4 is equal to 0, or lambda squared plus 4 is equal to 0, which means our eigenvalues are plus or minus 2i. That means we can get rid of all of our nonsensical eigenvalues right there. Let's just check plus 2i. So for lambda is equal to 2i, a minus lambda I will be negative 2i to negative 2, negative 2i. Let's see, let's divide everything by 2 and multiply both of these rows by -1. That's a little bit of a nicer situation here. And since our second row is saying that x1 plus I x2 is equal to 0, we can see that x1 is equal to negative I x2, and thus we can write this as a vector, our eigenvector as a vector of x2, where x1 is equal to negative I and x2 is equal to 1 of itself. So I got lucky this time. I didn't actually go down that road thinking we would get it, but you'll see that if we plug in our other conjugate eigenvalue, all that's going to change is the sign on the I in our eigenvector. So B is our answer for 21. And it's good to remember that it doesn't actually matter which one of these rows you try to solve to get your eigenvector. If we take I x1 minus x2 is equal to 0, we can say this is equal to x2, and then in order to get a coefficient of 1 on x1, we can multiply both sides by I, so we'll get -1 over here and I over here, and then multiplying everything by -1, we get negative I x2, which is exactly what we got through our other row. It just took a little bit longer. Which of the following matrices is not diagonalizable? So just to make sure that we don't have any preconceived notions of what's going on here, it's good to remember that diagonalizability does not imply invertibility, and the other way around is also true. So just because A is not invertible doesn't mean it's not diagonalizable. So what we're looking for is really to get two repeated eigenvalues. So an eigenvalue with a multiplicity of 2, that when we plug it into our A minus lambda I, we get only one eigenvector. because remember, a matrix is diagonalizable if its number of eigenvectors is equal to the dimension of the matrix. So if the eigenvectors can span R to the n. If they can span R to the n, then we can create some eigenbasis out of those eigenvectors and rewrite things in a diagonalized form. So let's solve some of these. If we're solving A for its eigenvalues, that will be 2 minus lambda times 2 minus lambda minus 4 is equal to 0, or lambda squared minus 4 lambda plus 4 minus 4 is equal to 0. And so this has eigenvalues of 0 and 4. So because we found two eigenvalues, each of those must have at least, or in fact, in this case, exactly one eigenvector associated with them. Therefore, we have two eigenvectors for this matrix, and it is diagonalizable. Skipping around, let's see if I can find the one that isn't. E looks promising, because if we find our eigenvalues here, we'll have negative lambda times negative lambda minus 4 is equal to 0, or lambda squared minus 4 is equal to 0. And no, I was slightly off there, because this will give us lambda is equal to plus or minus 2. Two eigenvalues means two eigenvectors, so that is perfectly fine. B, however, no, B is the real one, I'm pretty sure. If we take 2 minus lambda multiplied by 2 minus lambda minus 0 is equal to 0. This only has solutions for lambda is equal to 2 with a multiplicity of 2. And if we plug in that lambda, we will get 0, 0, 0, 2, which simplifies down to 0, 0, 0, 1. And so since this is saying as an equation that x2 is equal to 0, the eigenvector that we get out of this is 1, 0. And since we only got one eigenvector for an eigenvalue with a multiplicity of 2, the eigenspace associated with lambda equals 2 is not two-dimensional, thus blah, 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 all of the other things we were saying. And this matrix cannot be diagonalized as a result. So B is not diagonalizable for 22. 23, let's find x at 1, which is the solution to x prime equals ax. With this initial condition, let's solve for our eigenvalues. That's 5 minus lambda times 5 minus lambda minus 16 is equal to 0. And so we get lambda squared minus 10 lambda plus 25 minus 16 is plus 9 is equal to 0. So lambda minus 9, lambda minus 1 is equal to 0, lambda is equal to 1 and 9. For lambda is equal to 1, we get an a minus lambda I of 4, negative 4, negative 4, 4, which we can simplify down to 1, negative 1, 0, 0. And since this really means that x1 minus x2 is equal to 0, or x1 is equal to x2, if we are writing an equation in terms of our free variable, so x2, it's equal to 1x1 and 1 of itself. So there's our first eigenvector. For lambda is equal to 9, we get negative 4, negative 4, negative 4, negative 4, which simplifies to 1, 1, 0, 0, and by the same logic, we'll get an eigenvector of negative 1, 1 out of that whole exchange. So now writing our x of t, and this is not x of t just the solution to this x prime. This is x of t, both of these together as a kind of combined vector. This is c1 times our first eigenvector times e to the lambda 1 t, which is just t plus c2 times negative 1, 1 e to the lambda 2t. Solving using our initial condition, we'll see that 4, negative 2 is equal to C1 times 1, 1 plus C2 times negative 1, 1. So we can make a matrix out of this. 1, 1, those are our C1 coefficients. Negative 1, 1 for C2, and then 4, negative 2 there. Subtracting row 1 from row 2, we'll get 0, 2, negative 6. So this becomes 1 and negative 3. Adding it here gives us our answers for C1 and C2, where C1 is 1 and C2 is negative 3. And then all we're doing now is solving for x at 1. We have to be careful here because x at 1 is not the solution to this x of t that I've written. It's the top equation. So it will be 1 e to the t, pulling out this guy, plus 3 e to the 9t, and this is x of t. And plugging in t is equal to 1, we get 3 e to the 9 plus e, so e is our solution for 23. 24, let's consider this dynamical system x prime equals ax, where a is given there. What is the origin? So that's dependent on what the signs and types of eigenvalues we find are, so let's find those. We're solving 1 minus lambda times negative 2 minus lambda minus 4 is equal to 0, or lambda squared plus lambda minus 2 minus 4 is minus 6 is equal to 0, or lambda plus 3 lambda minus 2 is equal to 0, lambda is equal to 3 and negative 2. And because we have one positive and one negative eigenvector, that means that as t approaches infinity, our solutions will tend from following one of our eigenvalues, our negative valued eigenvalue, to our positive And I'm actually not sure. That might be the other way around. But either way, we'll get kind of this. If I draw it out, we have one eigenvector. I was also saying value, wasn't I? We have one eigenvector, two eigenvectors. As time goes on, our solutions will go from one eigenvector to the other eigenvector, and this is what we call a saddle point. So 24 is A. And if A is this huge matrix here, which of the following is a basis for the column space? Let's row reduce this, find which columns have pivot positions, and then come back up here and make a set out of those pivot columns. So we have 1, 1, 1, 1, 1, 2, 0, 2, 2, 4, 0, 3, 3, 0, 0, 4, 2, 2, 2, and 5, 1, negative 2, 4. And we're row reducing all of this. Let's subtract row 1 from row 2. 0, 0, 0, negative 2, negative 4. We can turn this into a 1, 2. Subtracting 2 row 1s from row 3, we'll get 0, 0, negative 6, negative 6, minus 10 will give us negative 12 here, so this is 1, 1, 2. Subtracting row 2 from row 3 will give us a 0, 0 here, so we can use that to set this 3 equal to 0. Then subtracting 4 row 2s from row 1 gives us a 0 here and a negative 3 here. Additionally, because row 2 and row 4 are just combinations of each other, multiples of each other, we can set one of them equal to 0 using the other. And if we rearrange these rows slightly, we are ready. There we go. We are ready to solve. We're ready to solve everything. So because We have a pivot here, and a pivot here. And look what happened. I actually did too much work. We could have seen which columns were pivot columns a lot earlier, but I just got a little carried away with the row reduction, and that can really waste useful time. So because we have pivot columns for columns 1, 3, and 4, 1, 3, and 4, these three as a set will form a basis for the column space. So that gives us answer choice D for 25. And we are done. Yeah, there we go.